Hey, what's up, guys? This is Chung here. So today, let's continue uh, with the LeetCode problems here. So today, number 100, sorry, number 1428, leftmost column with at least a 1. So you're given like a matrix, and the matrix is consists of 0 and 1s. And for each row, the matrix is sorted. It's sorted from left to right. Okay, so sorted means it's either zero, all the zeros on the left and all the ones it's on the right. And you need to find the leftmost column that has at least one number, one one. Mhm. If there's no ones at all in this matrix, you simply return -1. So for example, this one, right? So the column 0 has a 1 here. That's why we return 1 here. And this one, column 1 has 1. We return 1. Same thing here for this one, also 1. For this one, the column 1 has 1, so well, that's why we return 1. And so, and the difference here is that this problem is an interactive problem, which means you don't have direct access to this matrix here. All you can do is you have this binary matrix object where you have uh, two two method, right? First one is to get. Basically, you can only get the current row and column if the current row and column is 0 or 1. The second one is you can get the total dimensions of the column of the matrix. So since the matrix is not, it's only sorted on the row level, so it could be something like this, right? 0 0 0 1, let's see, 0 1 1 1, right? And 0 0 1 1. It could be like this, right? So I think the most intuitive way is like basically we sort we select what we we search each row. For each row we do a we call, and for each column element for on the row we get the we call this get for each element here, and on each row we maintain the leftmost uh index until we see a 1, right? So for the first time we see a 1, oh, we know, okay, basically we scan from left to right, and then we know, okay, so that's the leftmost column that has 1 for this row, right? And then we just loop through all the rows. In the end, we just return the minimum value, right? That's the brute force, right? Brute force. And the time complexity obviously is m times n, right? So, and the better search solution is to use a binary search, right? Since this for each row the number is sorted, right? Then it gives us like a hint, right? It's probably a very clear hint. Basically, for still we store scan each row, but for the specific row we don't scan each element from left to right. Instead, we do a binary search. We get the middle one and we check, okay, if the middle one is 1 or not. If it's 1, okay, then we know we can keep moving to the left. Otherwise, if it's 0, we know, okay, we need to go to the right side to keep looking for the ones, right? Okay, so I'm not going to implement that brute force one because that's the least efficient one. So I'm going to implement that a binary search, right? So uh, assuming we have this definition, we have a binary search. We uh, find most left one column. How about that column, right? And we're gonna pass the row here, right? Assuming we have this method, let's implement the main the main code first. Assuming we have this method, every time when we pass a row here, we just do can give us the leftmost row. So we simply do first we'll get the rows and columns, right? What's the rows and columns here? So we're gonna do a binary matrix dot dimensions, right? Dimensions. Right? That's the rows and column. And for each row, for row in rows, right? And uh, we have an answer here, right? Since we're going to get the minimum, the the leftmost index, so we're gonna initialize this answer to the max size here, right? And then okay, so mm, index, right? So, but remember, so it could be the case that there's there's no ones in this matrix at all, right? So in that case, uh, so the leftmost index, so we'll be using like a flag to to check this leftmost index. Uh, in my case, I use -1. Basically, if the leftmost index is equals to -1, then it means we didn't find the ones. We didn't find any ones in this row. So and we can simply skip that. So that's why we do a uh, if leftmost index is not to -1, right? And if this thing is less than the answer, right? Sorry, the answer, then we know, okay, this is the valid index. We just assign this answer to the leftmost index, right? And in the end, we simply return the answer if answer is less than sys max size. Otherwise, I'll just return -1. We know that we never find a valid index in this case, right? So now with this row here, right? So how about how to implement this binary search here? So binary search, we usually have left and right. Left is 0 in this case, right? That's the index 0. And how about the right side? The right side is the columns, right? The columns -1, right? So and while left is not equals to right, right? Well, left is smaller than right. What do? We do of course, that's the normal uh, template for the binary search, right? We do a if uh, binary matrix, and so basically the row is the current row, but the column we use middle, right? If this thing equals to 1, right? So it means that okay, so the current middle is 1, right? So but so the answer could be the middle one or the ones on the left. That's why we do a right equals to middle, right? Because we want to save this one because this middle might be our result, right? Else we simply do a left equals to a middle +1, right? And we're hoping we can return right here, right? But keep in mind here, right? Since you know for the normal binary search, we know there has to be an answer, right? In that within that range, right? But the the only the small difference here is that the in the range here it could be there could be no result at all, right? So in that case, so what's gonna happen? Basically, if you go through the code here, basically we'll never find one here, right? So the left one will just keep moving until the left one is equal to the right one, right? So that's if that's the case, right? If that's the case, we just simply check if the left one is equal to the right one, then what do? We have to check uh, return right uh, if uh, we just check the current right. We just check the right if the right one is the if the right column index column is one or not. Because currently the left equals to right, so it doesn't really matter which one we use. I'll just use right here, binary matrix, do a row and the right. So this what does it mean? It means that okay, so if this last one, if this last one is the is the one, then we know okay, this is a valid result. If it's not the last one, we simply return -1, right? For example, this one, right? You can see that only the last column has one here, right? So in this case, we just do basically the left will keep moving to the right, right? Until the left is here. Uh, I'm sorry, until the left is here. Until the left is like, because we're doing a left less than right, which means when the left and right is the same as the last one, we will skip this. We'll skip the this for loop here. I mean, you can. I mean, I think there's a like of course there's obviously another way of doing this because you can just do a left less or equal than right, but then in there you can simply check do a check here, right? Um, yeah, basically that's a different template of the binary search. Instead of less than, we do a less or equal than, left and right. But for me, I just want to do it in this way. I'm kind of used to this like template. That's why I want to do this. So, but in this case, I need to do a corner case check here, right? So when the left is the same at the right one, right? I need to check if this one is one or not, right? If it's one, then we know okay, so that's this right is my answer. If it's not, then we know none of the basically there's no ones in this row. I just return -1 here, right? So that's how I implement this binary search helper function. And so with that in mind, with that being said, I think that's it. Let's just run it. Uh, for oh, it's an integer range. Sorry. Binary is not callable. Oh, sorry. Got. Yeah, what am I thinking here? Okay. Yeah, so it works. So and yeah, so the time complexity are very. I think it's kind of obvious. It's m is the m right times the log n right. Right. M is where m is the row, and then the count of rows, and n is the columns, right? Because for each column, sorry, for each row, we do a binary search, which is going to be log of n, right? Okay, so that's for the binary search. And can we do even better than the binary search, right? The answer is yes. How, right? And okay, I will try to draw another diagram here. Let's see. Hmm, 1, 1, 0, 0. How about this? 1, 1, 1. 1, 0, 0, and 1, 0, 0, 0, 0, 0. Yeah, because I keep in mind every row has to be sorted, right? How about the last one? I will do yeah, this one, 1, 0. Sorry. Okay. For example, this is the matrix, right? So what's our final answer? This one, right? This is the final answer. So how can we do a better approach here, right? I think you have to make some observations here. So first, we need to start from top right corner. We need to start from top right corners, and then we scan down and the left, and then we're trying to go to the bottom and left corner. We scan from top uh, upper right to bottom left. So how, right? So basically every time when we see a 1, when we see a 1, we'll move to the left. It makes sense, right? Because when we see a 1 there, we're assuming, okay, so this is the current 1. We want to see if there's like a 1 on its left, right? So that's the greedy. It's kind of greedy. You can say the greedy, or like, I don't know, the whatever you want to call it. Basically, every time when you see a 1 here, you move the index to the left. And if you see a 0, okay. If you see a 0, okay, so this row will not have any ones because they're sorted, right? So as long as you see a 0, okay, I'm not going to get a smaller column of 1 on this row. That's why I'm going to move down. Okay. So then you move down, right? You move down, you see another 1 here. You see another 1. And then what? Okay, I see another 1. I'm going to move to the left. Okay. And then it's a 0. Okay, so let's keep going. 0, it's not. Okay, I'm going down here to here. So and then let me go to left one more time. We see another 1. We go here, right? Then we see, okay, it's another 1. Okay. Oh, it's another 1. Cool. So I'm going to here, right? Then if it's 0, we go down. Another 0, we go down, right? And then we see another 1 in the end, we just go left, right? As you can see here, so basically we'll have two variables. First one will be the current row. Second one will be the current column, right? So in the end, we can just use the current column to so basically the current column will give us the final result because we see this one has moved to the left how many times? 1, 2, 3, 4, 4, and 5, right? But this 5 in the end is the last one will be do a -1 because the so when the whole process finish, uh, the current C is at here, right? Is at here. That's why in order to get the 1 index, we have to do a -1. Do a -1. Yeah. Sorry. I need to do a +1, not -1, because this current index is decreasing, and in the end, we just need to do a +1 to get our final result, right? So in this case, right, so all we need is we just loop through. Basically, we either go left or we go down, right? And how can we check? How about in the how about for example this like exception for this exception, like how can we check if what if there's no ones at all? So if there's no one at all, so what's gonna happen? It means that we will never go left. We just keep going down, 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 down until we reach the end. So in the end, we can simply check if this current uh, column index is the same as the length here. If it is, then we know we never find a one. So we'll just return -1, right? Yeah, so okay, and yeah, can we do this from here, from bottom right corners? Probably not. Yeah, I think from here we go. I think we can. Yeah, I think we can also start from here, right? Same thing, right? Same thing. If we see a one here, we we go left. We go left, and then if we see a zero, see a zero, and then we go up, right? Same thing. Yeah, we can either start from here or from here, right? Okay, cool. Anyway, so I'll just code, assuming we're starting from this top right corners, and let's take a look at this code here. And I'm going to just remove, or I'll just comment out this thing. Yeah, because I don't want to lose my precious code here. Okay, so same thing here, right? We're gonna have the rows and the columns. That's for sure. And what's gonna be our starting point, right? So starting point, the current row is the 0, right? Since we're starting from the top right corner, and the current column will be the columns -1, right? Then we just simply we keep uh, going down and left. So and when we are we going to stop, right? While what current row uh, it's sorry smaller than the rows, right? And current column is equal greater than 0, right? That's when we reach the bottom left corner, right? Before that, we will just keep doing it, right? So then we just simply check, right? If binary matrix dot get, right? Get the current R and current column. If it's 1, right? Like I said, if it's 1, we move to the left. Basically, the current the column will be decreased by 1. Else, we move down by decreasing the rows variable by 1, right? Okay, and then in the end, right? In the end, what's gonna happen here? So right, so we return the current column if the current column is smaller than the columns -1, right? Which means this thing, if this thing ever got moved to the left, then we know, okay, we saw a one at least once, right? Otherwise will be like what? We'll just return -1, okay, right? Yeah. So if there's no, if we never saw a one, then this current column will be the same as the columns -1, right? And then we know we never there's no one in this matrix. We just simply return -1. Okay, so let's run it. Oops. Ah, so embarrassing here. Uh, get binary matrix get current row, current column. Let's see. I think there's a boundary check here. Hmm. Oh, sorry, here. Okay. Plus one, right? Because we're going down. Going down means we increase this thing, not minus one. Okay. Oh, sorry. So like I said, in the end, right? In the end, this currency is on the left of our final answer here, right? So in the end, we need to return current this index plus one, because the last time we saw a one, this thing will be moved to the left, to this one's left, right? That's why we need to do a plus one in the end. All right, hopefully you can pass. All right, cool, pass. All right, so yeah, so I think that's basically the second solution. So the time complexity for this one, what's the time complexity here, right? So it's gonna be rows plus columns, right? There's no multiplication here, because every time we either move to the left or or down, right? We either move to left or to below. That's why the worst case, not the worst case, the every time it's always rows plus column, because we're moving from the top right corners to the bottom left corner, right? So the total distance, the total movement we'll make is we basically we move down to this distance, and then we move left to this distance. That's why the total time we spent is the length of rows plus the length of columns. All right, cool guys. I think that's yeah, that's everything I want to talk about for this problem. Yeah, I hope you guys enjoyed the videos. Thank you so much for watching it, and I'll be seeing you guys soon. Bye bye.